Okay, so I'm going to talk a bit about the RISC-V Linux port. So RISC-V is all the rage now, so I guess that'll be easy. Be kind, you know. Yeah, I just duck here, so we'll see. But Christoph, you like it, right? Great, great. Okay, so being the starting out the talk or giving the first presentation, that's a big task. It's sort of like setting the tone of the whole conference. I'm a bit nervous actually. Like, will this be okay? So just a heads up here. Like, these slides are horrible. So I don't want these slides to sort of set the tone of the conference. So just keep that in mind. So I was thinking, I'll do a little bit about like what is RISC-V and like why is it great and or why is it not great, and then a little bit short history, like what happened in the past, like how old is the port and stuff like that, and then a little bit about like what I'm working on now and what's the sort of next thing for it. Okay, so I'll start off with a narcissistic slide, which is about me, and everybody loves that. So my name is Björn, if you didn't realize. I've been dabbling mostly in various networking stacks over the years. I think the longest stint was at Intel, where I was doing mostly networking drivers and BPF. Then I moved from Stockholm to Gothenburg, and I was sort of fed up sitting in my basement, so I joined a VPN company called Mullvad, where I was working on WireGuard things. So I spent a little bit more than a year there doing that. And then a friend of mine, which is also maintainer of the RISC-V port, Palmer Dabbled, reached out and said, we have this new startup called Rivos, and we're trying to build a high-performance RISC-V core to compete with the Intels and the Apples, the AMDs, and all that. So I was like, that'll be fun. We'll see if that works out. So I'm there now. So we're still in this stealth mode, so I can't really tell what we're building, but we're trying to build a high-performance core based on RISC-V. So Rivos comes from, it's RISC-V and open source. So everything we do, try to be upstream first, and even down to the firmware level and everything. So that's the grandiose plan, at least. Oh, and if you have any questions or opinions or whatever, just scream out so we can sort of have a dialogue instead of me just rambling here on stage. Cool. So I'll do a little bit of whirlwind tour, what RISC-V is, and sort of what's the and why is this a thing now? So the most important part is that it's pronounced RISC-V, so it's not RISC-V or anything. So it's RISC-V. For me, the big thing with RISC-V is that it's a royalty-free, open spec ISA. So you can just take the spec, you can do an implementation, and nobody will sue you or harass you about that. You can just take it and run with it. So it's a bunch of specs. The specs there's both the ISA, which is the loads and stores and compares and jumps and whatnot. But there's also non-ISA specs, for example, interrupt controllers or IOMUs, for example. The spec is kind of, as an ISA, it's kind of boring. It's like there's nothing new added, really. It's just a variable length RISC-ish ISA. So maybe I should sort of pause on that a bit. Like, what is RISC? So RISC stands for reduced instruction set. But to be honest, there's not many like reduced instruction sets out there. ARM is definitely not reduced. There's tons of instruction. RISC-V definitely not. We have loads of instructions. So what is RISC? Well, everybody have their own thoughts what it is. For me, it's load store architecture and fixed length instruction, which is RISC-V is obviously not. We have both 32-bit instructions and 16-bit, which is sort of smells like thumb, to be honest. And also, there's the V instruction set, which is an extension, vector extension, RISC-V. That's that's not even RISC. It's definitely CISC, and I would say that's true for SV as well. There's nothing RISC about that. Cool. So okay. So the idea is that you have this organization called RISC-V International that it's like a collaboration between companies, and we try to build these specifications. So you have a bunch of specifications that you can sort of, some are compatible, some are not, and then you can mix and match. But you know, that sort of smells of fragmentation. So the idea now is to try to group that into something we call profiles. So like a server profile. We have a microcontroller profile. And I think similar to what ARM has, right? No one is nodding. Okay. Anyway, so RISC-V tries to cater from both, I mean, the whole spectrum. So from really tiny MCUs up to, you know, HPC, which is like a high-performance cores. So microcontrollers to high-performance computing. And will that work? Well, we'll see. So really, what is the fuss? So why is this like, okay, it's yet another ISA. Why do we care? Well, to me, it's like the big thing here is that we have, like the specifications are open and anyone can really just take them and implement the core. So for example, say that you're a startup and you want to use a soft core on your FPGA. You buy it from a vendor, and after a while think like, hey, I want to implement this myself. Well, good luck with that. If you're not like based on a open or royalty-free spec, then you're pretty much, well, you're not allowed to implement this spec yourself because it's our ISA. So for me, it's a like big flexibility, and also if you you start with building your core, and then maybe you want to sell your IP to someone else, you can do that. You're free to do that, and that's for me that's really the big win. And you know, specs are boring. They're boring to write, but they're really it's sort of the basis of innovation. So you have a spec, and then you build on top of that. So for me, that's really powerful. And one thing that always comes up, there's this great forum called Real World Tech, where it's supposed to be a hardware forum, but it's mostly like software people trying to be armchair hardware architectures. So and people like, yeah, this ISA, it's the worst and whatever. It's like, is it the best ISA? No, it's not. I mean, it's lots of warts and, you know, some things. For example, one thing that I hate is the compressed, like the thumb-like, which is, you know, that's a mess if you want to build a high-performance core. But it makes sense for microcontrollers, for example. So there's a bunch of things that are not good. But the thing is, it's open, and we can all the involved companies are learning how do we sort of build specs that we can reuse, and we sort of are not tied to one company. Because right now, I mean, honestly, all the ISAs out there, like ARM and Intel, you're sort of sitting in the lap of these big companies, and you have no, like, that's what it is. You can't really get rid of them. So hopefully, this is a way out. We'll see. So it's definitely not the best ISA, but we might be at some point. And this is just some quotes from, I think it's kind of interesting. Like a bad sign is when if you start suing your customers, that's usually a bad sign. So so Qualcomm said like, hey, okay, story like this. So Qualcomm bought this company called Nuvia, and Nuvia's grandiose plan was to like implement a high-performance ARM core similar to what Apple does, and then sell it. That was the plan. So Qualcomm thought like, hey, this is seems like a solid team. Let's buy that company. And ARM said like, hey, you can't do that. Like, you're not allowed to. So they actually sued one of the biggest customer. And to me, that's like, it's sort of a bad smell. So now there's a bunch of companies like Rivus. We're doing RISC-V, and there's a bunch of other companies as well. And this is sort of an interesting quote from Jim Keller, which is the founder of TensorTorrent, like an AI startup. And pretty much like we don't have to ask for permission. We can just build it and run with it. Nobody's coming after. There's no, you know, we don't have to hire a whole legal team just to, you know, do engineering, which is, to me, that's a big thing. Okay, I guess the sales talk is over. Any questions or thoughts or? Nope. Okay, so now to the Linux port. So the Linux port for RISC-V is 6 years old as of a couple of days ago. I think it was May something. Yeah. It was probably merged later. Anyway, this was the first, like, hey, Palmer wrote this mail. Hey, we have this port, and Albert and I will maintain it, blah, blah, blah. So that's the first step, and it's 6 years ago. So what happens since? Or this is like, early porting. Palmer is, by the way, he's still a maintainer, and Albert is still a maintainer, but it doesn't really do much noise. So if you look at sort of the boot process of RISC-V, like where are we at now? So from an ISA perspective, I think RISC-V is pretty mature from a like MCU or really small core perspective. I would even go as far as say it's a no-brainer to, if you have an internal like an internal machine or internal thing that you want to run a CPU on that's not facing any customers, like you can sort of, architect your own instructions, and you own all the source and everything, then it's a no-brainer to pick RISC-V. Like, you have all the tool chains, everything just work. It's just less work to pick RISC-V. So I would say like RISC-V has actually won on this. So I was talking to one of there's a fellow at AMD who's designed Microblaze, which is this soft core. And he said that all the internal IPs at AMD, they're moving to RISC-V. So every time you want to replace like an internal, like weird Synopsys, Arc, whatever core, they pick RISC-V instead. So, and that's kind of interesting. I mean, so internally, a no-brainer. What about the embedded Linux side? What we sort of love and use, Linux with the device tree. I think that's sort of work. There's products out there and people are running it, so pretty good. If we start looking at the server side, which is where I'm at right now, it's a lot of work still to be done, and it's still, I guess, we still need to prove if it's good enough for servers. So what is sort of missing in RISC-V now? And especially in Linux. So, for example, like servers need, proper interrupt controller architecture, and this is the IAI thing. It's Advanced Interrupt Architecture. A lot of acronyms. It supports things like MSI, which is message signal interrupts, and also virtualization of the interrupt controller. So if you want to run, virtual machines, stuff like that, you need like a proper interrupt controller spec, which is similar to what's the ARM equivalent? GIC version 3 maybe, or 4. ACPI and UEFI. People love to hate ACPI, but to be honest, if you want to run things on servers, you really need ACPI. There's hot plugin support in ACPI. If you want to piggyback on a lot of existing work, for example, CXL currently doesn't have any support for device tree, so you sort of have to use ACPI in order to be able to run CXL. There's a bunch of security features, which is like KSLR and CFI, and all those things that you are sort of getting used to from the ARM and Intel world. What else? Yeah, supporting on modern things like, CXL, hot add remove, and then trusted execution, which is, I'll get into a little bit. And this is sort of running, like how do you run a secure or confidential virtual machine? Cool, so I figured I'll just, pick a couple of series from the 6.4 release, which I found interesting, but it doesn't really, they're nothing advanced or anything. I just find it like interesting to see where sort of the RISC-V tree is moving and what it's like what parts when an architecture sort of grows up, what things sort of tend to move around, if that makes sense. And then bugs as usual. Most of the fixes are just bugs. So I'll start with this one. So which is kind of boring thing, but necessary. It's a relocatable kernel, and that means that you can sort of load the kernel anywhere in memory. And this is sort of like a prerequisite to use KSLR. And KSLR is when you sort of so kind of interesting. So what is it? What this series? It's pretty much you build the kernel with position-independent code, and then you end up with a little snippet of relocation code at the boot, and that's it. But this is sort of the basis to build the next thing, which is KSLR, and it's kernel address space layout randomization, maybe. So that is that you can sort of place the kernel both like with a random offset. So for so typically like device tree or the firmware give you a seed, and then you randomize where the kernel resides in memory. And if you're booting with UEFI, you can actually randomize the physical location as well. So you can both have random physical location and virtual. What else? This is kind of interesting. I love these kind of commits. This is like, you have all these architecture-specific code, which is, and to be honest, most architecture look the same. So this is just a nice cleanup. Like you move, for example, when you do a fault or an interrupt in the kernel or a syscall, you have to do a bunch of things, which is common for all the different architectures. And up until recently, I think it was Thomas Gleichner that added this generic thing. Everybody has to sort of implement it, or everybody was implementing it themselves in the architecture port. So what this does is just moving a bunch of assembly things out and makes things much easier to read. So for me, this is like the best kind of commits. Like, you do a couple of change and you just delete a lot of stuff. So this is great. And it was done by Guren, which is, I don't know, I mean, he's at Alibaba, but I think the company that Alibaba acquired was T-Head, and it's T-Head that's building the course. Did I hear something? Yes? No? Okay. Cool. This is kind of interesting, and probably this would be interesting to hear from the ARM people what they sort of did. So this is one thing with RISC-V is all these. Okay, there's all these extensions, and so the grand plan from the beginning was to let's just use single letters, and we have G, C, and V. This means G means the base instruction set and stuff like atomics and stuff like that. C means the compressed one, and V is the vector one. All good, but then reality happened. So when the Linux port came out, for example, some of the specs weren't ratified, and ratified means like they get a stamp of approval. So this means that, so we have like version 1, and then we'll get version 2. So what does like V really mean, or what does I really mean? And then at some point, like the standardization, this RVI, or RISC-V International, I call them RVI, they actually removed, they removed this guy, the Xiphens I from the spec. So now if you say RISC-V with I, like what is that? We don't know. So now, let's add versioning. So now you can, like this is actually a thing that you can pass to the compiler. So X and X means, so right now what happens is that all the specs has been split up into all these extensions, so and this is getting out of hands. And if you, and to be honest, this is not the longest one. I mean, this is, and obviously this doesn't exist, but it would be nice though. So everything with an X is your own extension. And if you want to see what the compiler supports, for example, if you're running LLVM, you can run this thing, and it'll spit out a bunch of extensions. And then so they try to do versioning, but then the hardware folks, they're like, we don't care about software as usual. So some versions were like a Git-SHA 1, and like one version was RC, and like let's ratify the RC. Bam. So I mean, this string couldn't really be parsed. So what happened is like the Linux maintainers, they were crazy, or still, I mean, they're still angry, to be honest. So it's like, how do we cope with this? And I think it was at last Plumbers sort of said that, okay, let's just do something really simple. Like we add a syscall that is just a key value store. And you can just ask for capabilities from via that. So it's something really simple. And we sort of, we as the kernel decide, okay, what things are compatible from a kernel's perspective. Like if someone says I, what is I? Well, it's I without this I fence extension, for example. So we'll see this this made the standardization folks really angry because, hey, we want our long string, but we said like we can't parse it, but you got the long string, and there was a lot of back and forth. So we'll see, but this is upstream now, so now we can actually use that. And I think, I mean, all the architecture for Intel, for example, they use the CPU ID, and I don't know about ARM, they probably have something similar, like, right? And ARM people here? How do you how do you sort of figure out what a core supports? Yeah. And and obviously RISC-V has the uglier side there because we have all these extensions and splits. So yeah, so we'll see how that. So that's the current plan. So that was sort of 6.4. So, and in terms of like RFCs and you know what else is cooking, this series is from a colleague of mine, and this is sort of trying to define what would confidential compute look like in RISC-V world. I think I just leave it at that. There's a lot of discussions going on with that. So it's and you know we try to sort of tie it into what the ARM folks at Google are doing with the is it PKVM? Yeah. Yeah. So we'll see. I'm not really involved in this, and it was like a huge series, and people were kind of angry actually. So I tried to stay away from that. Cool. The other thing is ACPI. So ACPI is like, if you want to learn how ACPI works, I think now is a really good good time to look into it, because this series is about to be upstreamed, and it's a really small series. It doesn't do much. It's just the basics. Like there's no external interrupts. There's no PCI support. So if you want to sort of wrap your head around like what is ACPI, now is a great time actually. So if you want to, yeah. But it's yeah. I mean, if you're sort of have that, I mean, you know, it's an acquired taste, to be honest. But it's, I guess, you know, when I started Intel, I didn't really like it. But then, you know, the grind sort of made me like it. So no. What else? Vector support. This is Vector, and you know, this is our favorite villain, Vector from Despicable Me, and he's typing with his butt. And this, maybe it's sort of, I mean, this series is version 20 now, and it's a lot of discussions about it. So I just think it was really close to be merged, but I figure I'll just spend a little bit of time why it's hard to adding like a new extension sometimes. So short about Vector. Vector adds like 32 variable length registers, similar to what SV does on ARM. So, for example, you can have a register which is, I don't know, 2048 bits. And then the idea is that instead of having these fixed registers, you can sort of change the size of them. So you can like tell the hardware, hey, act as if this register was 256 bits instead of, yeah. So that's the idea. So that's a software can sort of determine or decide what's the bit length for this current implementation. So I mean, from a kernel's perspective, what this is like it adds some things to the context switching, but the big pain has been this, is like the signal frames, which is kind of interesting. So when you start out with a port, you define your like the structure. The structure of the signal, which contains all the registers, is a user API. user API. So that means you have to sort of think up front, like how much will I add later, for example. And in the RISC-V case, we didn't realize that that we would need more. So our sort of signal struct is too small. So that means we get a lot of breaks. So, for example, if you have an old program that is using this, like for example, the get set context, which is a really arcane and old POSIX API, you can actually get the signal frame crammed in between two structures. So that means like if you grow it, you pretty much you break the you break that code. Then we had back and forth, and if you squint your eyes, we could work around it. But then it happens that one person showed up like, I'm doing this with the signal handling, and so they were running. I think this was on the glibc list. So they were doing like user space task switching. So the idea is that like you have a sig timer and you get an interrupt or you get a signal, and then you sort of switch. So you do sort of short circuit the return from the signal via the sig return system call and change that. So, and with this new addition of these extra registers, the assumption was that when you get a signal, you will have the whole register set in the signal. But if you add registers, you won't. So that means if you're running this code and your glibc is running a vectorized memcopy, for example, and you get a switch in that vectorized memcopy, this program broke, which is kind of like, okay, it's, I was hoping, RISC-V was still early days, but as soon as something, it's 6 years, and as soon as something sort of enters the upstream, people start building weird stuff, and you're stuck with legacy forever. So, and this is what we're trying to. So what happened now is similar to what Intel did with AMX. And AMX is the matrix extension for Intel architecture. So you add a bunch of registers as well. So right now you have to explicitly turn it on. So we'll see what happens with the vector if we actually want to explicitly turn it on, or if we want to trap enable it, and is that okay, or given that these applications will break. So yeah, it's kind of a mess, and we'll see. I think the verdict's still out, what the final version will be. So it's version 20 and counting. And then there's sort of my favorite topic, which is text batching. This is, RISC-V doesn't even define how you are supposed to behave when you text patch. So right now it's like, the kernel does it in, I think it's 4 different ways, and it sort of works sometimes. So it's, so I'm really hoping that we can, I'm working on something just to document what does the kernel do. Let's try to make it the same everywhere, and then maybe try to get a spec for it. That was sort of everything I had. So it's, I think, if you fell asleep and woke up now, I would say like one thing to take away, like what I really like and why I sort of got into RISC-V was that it's a great way of learning the kernel, especially this. I mean, 6 years is still a young port, so it's a great way of just figuring out how things work, like where are the problems and how does things break in weird ways. So if you just want to play around it at your spare time, which is how I started, I really encourage you to do that. And also, if you want to just talk or submit a patch or whatever, we have this a Google Meet thing, which is every Wednesday at 4 o'clock Swedish time. And there's also a couple of people, ranting on the RISC. So if you want to, just hang around and talk or, ask about things, it's still a small community, and we're still kind of friendly. I don't know. So that's it. Questions, thoughts, tomatoes. Yeah. To be honest, I don't know. I don't know. I guess. Was that me? Oh, I think maybe. I guess the hope is sort of see if that thing, if it sort of solves over time. I guess when maybe we'll see some kind of consolidation, but when people get actual hardware out, and then that will sort of create a natural baseline maybe. But right now, I mean, I don't have any answers for that. I'm worried as well.
It could be quite a bit of headache in a lot of different technologies and so on.
Yeah.
I mean, it's
yeah. One thing that I actually forgot to mention, which I was talking about, was forgot just a simple thing as distro. Like when you build a Debian distro, like what extensions do you support? Because right now the situation is that, for example, I'm a Debian person, so I don't know about Red Hat, but it's probably the same. I mean, we use the bare or they use the bare minimum of the specifications, and that's like it's too little. And I mean, an alternative is to resolve everything at runtime, which is that's not possible as well. So we'll see. Hopefully, somebody figures it out. But it's my hope is that it'll evolve sort of over time. But it's a crappy answer. I know. It's a non-answer.
Background here is I'm from Linaro, and we have been working with ARM for many years, and trying to address these kind of open source problems in general, and that's just software. And now I see the same kind of thing repeating with RISC-V. I mean, you have everything is open, and it's great because I can do whatever I like, and that's good for 1 year or 2 years, and then suddenly you realize, well, I'm actually dependent on these guys and these guys and these guys, and we need to agree on how we should do things and so on. And that's why I'm a little bit curious to see how the RISC-V community is approaching these kind of questions nowadays.
And to be a little bit critic, I think, the RISC-V community has sort of failed to learn a lot from what ARM did when they, with ARM 7 and the whole Linaro debacle. So hopefully, we'll see. And there's a lot of times when you just, hey, this is what ARM was doing 10 years ago. Yeah. Like we're doing the same mistakes. So we'll see.
Yeah.
Hopefully, we'll learn with this process of trying to have an open spec and also, or maybe it just end up as a mess. We'll see. Anything else? Anyone more?
So there's so many RISC-V companies trying to do high-performance compute. So are you probably not going to be able to answer like Ventana, Rivers, Sci-Fi? Who's going to win?
That's the easy one. It's obviously Rivers, because the other ones are, they're just tomtar or just, gnomes. Or they're just playing around, whereas we're doing the real work. We're the adults in the room and all that. So that's the easy part. But we'll see. I think jokes aside, I think the closest one to a actual tape out is Ventana Micro, and they claim to have silicon work. I think it was some GCC maintainer that said that they got some test chip running and building. So I think they're the closest. I haven't seen any performance numbers. And then there's the Tense Torrent. They're also building a high performance. They claim, and they have all these super fancy sales graph where it breaks the scale and hockey sticks and whatnot. But they haven't taped out yet, so we'll see. There.
I was wondering, maybe this was also answered somewhere alongside already. If the ISA is defined, does this include the pipelining structure, or is it like everyone who's creating his own RISC-V implementation can choose how to optimize its instruction differently when it comes to compiler optimization and stuff?
That's completely out of spec, and that's sort of where companies innovate or like so. Okay. So it's nothing like that is defined. And
okay.
And personally, I think that's a good thing. It's sort of open up. That's like you can go to different vendors and they have different implementations. So it's just the ISA and the non-ISA.
But won't this make optimization from the compiler side very hard, or is this not such a big deal?
I guess the verdict is out. That's also where we're. But it's.
But that's not really different from what you have between Intel and AMD, for example.
Maybe not.
Various ARM implementations including weird binary translations to other underlying things, Icadium.
I mean, usually it shapes by effect to see how fast an instruction is. I mean, it's not, we can't deal with this if it's all the same either.
Okay, down there. Be kind and stuff.
Well, I mean, this also goes back a bit to the previous discussion, right? I mean, when you do all these little weird extensions, that's probably more of a headache for generating optimized code than slightly different pipelines, unless you were doing like really high throughput vector floating point operations or whatever, which again gets you back to all the extensions you actually need there to get performance anyway. Yeah. But as people said, this is not a new thing, right? I mean, ever since the early 90s, you generally have widely diverging implementations for microarchitectures, and if you go to mainframes, it even goes back to the 60s. And that's not new. It might be something some of these startups don't grasp, that they really need someone who understands Clang and GCC optimizations, and they don't just have to design a pipeline. But if you look at GCC, the amount of tunings it has for various x86 microarchitectures or ARM or MIPS or that's not really new. What is a bit new is the weird extensions that are even more unorganized than in other architectures, even if a lot of good groundwork has been laid by other architectures in making a mess there. And one interesting thing that happened on x86 in the last years between Intel and AMD and I think Red Hat is that they started defining x86 64 base levels 1, 2, or 0, 1, 2, and I think 3.
Yeah, 3 as well.
Where it says, okay, if you target x86 64 3, you need, I don't know, AVX 256 and this extension, that extension. And I don't think RISC-V will get around this, and I think we're at a point where it starts making sense thinking about these base levels, because now a lot of these important extensions are done that weren't part of the original spec, and you kind of see what gets adopted or not. At the same time, we still have giant mess in some areas where people don't implement the official cache flushing instructions and come up with their own mess. Yeah. And yeah.
And also just different versions of the spec.
Yeah.
Like,
but I mean, different versions of the spec is easy, right? The problem is when you have these micro extensions, and RISC-V seems to gravitate towards these micro extensions. Yeah. I mean, x86 has too, right? And then you just need to start grouping them in sensible groups. This is what I expect for an HPC chip. This is what I expect for a low-level, like a low-end SoC that doesn't have cache-coherent peripherals, but might do interesting thing for small code size, yada, yada, yada. So.
Well, isn't already there with the G means that you have some specific...
Yeah, it's a baseline, but well, like, is it the correct baseline? There's a bunch of things missing, to be honest, but it's... yeah, we'll see. I think Crystal said we'll probably get some kind of profile, maybe ad hoc or defined, but it's, I mean, from a distro perspective, it'll be interesting as well. Like, how do you ship a distro with, for example, the x86 different profiles, like 1 to 3. I think the only one that's doing that now, I mean, obviously glibc has all this thing built into one thing, but OpenSUSE has, actually, you can sort of select packets based on the profiles, maybe with that. But then we have the kernel, like, how do you select extensions in the kernel? Like, do you want multiple kernels? I don't know, we'll see. Yeah, exactly, yeah. We were talking about at the dinner yesterday, so what's the name of the guy that wrote QEMU? Fabrice Bellet, yeah. He had this really nice hack where he was using TinyCC and a bootloader to actually build the kernel just before it booted. So I mean, maybe that's the right way of doing it. You just invoke GCC for every boot. I mean, why not? Okay, I think I'm out of time. 40 minutes.